Okay, so this one we're doing escape velocity, and we want to see how does the escape velocity change if we are doubling the density and a third of the radius. So we want to see how does the velocity get changed. So I hope you're thinking, how do we write an equation for escape velocity? So I know escape velocity is, if I have an object on the surface of a planet, I know it needs to have enough energy to get away from that gravitational attraction, trying to pull it back towards the center of the planet. So if it's moving, we know it's going to have kinetic energy, and that kinetic energy is 1/2 of m times its speed squared. So we need to have enough speed, enough kinetic energy to overcome that force of attraction trying to pull it back. And we know that force of attraction pull it back, right? We know if it completely escapes the planet anyway. If it completely escapes the planet, we know it's going to be at zero potential. So we know it's the gravitational attraction trying to pull it back. So we know there's an equation on your formula sheets that change in work is the mass times by the change in its potential. So it's going from a potential line on the surface of the Earth to a potential of 0. So that's whatever the potential is on the surface of that planet. I said Earth, I apologize. Whatever the potential is on the surface of that planet, that is the change of potential, because we're going from that potential to 0. So that's just the change of potential. Because anything take away 0, it's just the same number. So I know then to find that change in energy, it's the mass times the change in potential, okay? Now we just said the change in potential is whatever the potential line is on the surface of that body, okay, of that planet. So we know that potential is gm over r. So what I'm going to say now is its kinetic energy needs to be greater than the work done we need to pull it, the work done it needs that's getting pulled back down towards the center of that planet. So technically our kinetic energy needs to be greater than that work done that we would need to remove it away from that planet, right? The energy is trying to pull it back then towards that planet. So that's that mg m over r. So the mass of my object cancels the mass of my object, and then I can see that v squared is going to be equal to, so we set them equal to look at the extreme, 2 times gm over r. So to find an equation for v, I can see this escape velocity is equal to the square root of 2gm over r. But the question says that we're going to third the radius. That's easy to do because I've got radius here. But it says the density is doubled. But I don't have density as an equation. So I'm thinking, how do I get density in the equation? Now I know that density is equal to a mass divided by volume. So I've got a mass here. So what a mass is going to be my density times my volume. So my mass is going to be my density times my volume. We're going to model the planet as a sphere. It'll be 4/3 of pi r cubed. So what I have now is the speed is equal to the square root of 2 times g times the mass, which is the density, times 4/3 of pi r cubed divided by r, so it becomes pi r squared. Now, what it says is that we know the density has been doubled, so the density new is going to be 2 times of the density old. And it said that the radius is a third. So what I'm saying is the radius new is a third of the old radius. So what we're saying is our density is getting multiplied by 2, and our radius is getting divided by 3. But the radius is squared. So again, if the radius is squared, but my new radius is divided by 3, and then we square it, really what we have is my radius squared over 9. So what we've really done is we've dropped this fraction by a factor of 9. But again, it's inside the square root. So we've multiplied by 2 and dropped by a factor of 9, but it's all inside the square root. So what we have now is a square root of 2 over 9. And the square root of 2 over 9 is going to be root 2 over 3. So root 2 over 3 gives me that option.